Unit 3, forces, is all about, force and applying Newton's 3 laws on a variety of situations, taking each of Newton's laws one at a time. Law of inertia states, as it's stated here, objects in motion stay in motion unless acted on by outside and unequal forces. And the same goes for objects at rest. Objects at rest, you can apply a force to it, but if your applied force to that object is equal to that force of friction, then that object will not move. Meanwhile, objects already in motion, if all the forces acting on that object are equal, that object also will stay in motion. It will experience no acceleration as long as our force of friction and our push force, perhaps applied by that motor, are equal to one another, known as the law of inertia. Newton's second law is just known as the Fermat triangle. I think that has a long-winded explanation. The force of an object is directly proportional to the mass and acceleration of motion experienced by that object. But putting it simply, we just say force measured in newtons is directly proportional to the mass in kilograms, which this is going to lead to some heartbreak this year. This mass here is in kilograms. So if you're dealing with something in grams, you got to convert it to kilograms before you plug it into this equation. And your acceleration is meters per second squared. Okay, so if we are dealing with a frictionless surface and we apply 20 newtons of force to a box on that surface, your acceleration experienced by that box is going to equal to 0.66 meters per second squared. Meanwhile, if we apply the same amount of force to this box over here, you get a much smaller acceleration. I know that a lot of this is logic and we're just putting math to what we already know, but that's Newton's second law of motion. Force is equal to mass times acceleration. Third law of motion, for every action there's an equal and opposite reaction. We use Newton's third law a lot this year. When I used to teach 8th grade, we would do balloon-powered racers. You'd fire a force going this way by letting air out of the balloon. It would provide that reaction pair force drawing motion that direction. It explains why providing a force downwards in the case of space shuttles launch them upwards. But most importantly, as used this year, there's a force that acts on every object perpendicularly downward, if we can draw it perpendicularly downward, known as gravity. But, if you notice, you don't fall into the table. The object doesn't fall into the table. You don't fall through the floor. That's because there's this really important force that we'll talk about a lot this year called the normal force. The Newton's third law action-reaction pair force, which keeps this object motionless and not falling through the table. And honestly, the rest of the unit is just applying those 3 laws in a variety of situations and circumstances. For example, if you're pushing a box and the box has a mass of 20 kilograms, and you're going across a frictionless surface, what's the net acceleration experienced by the box? Questions such as this. You're normally tasked with building what's known as a free body diagram, in which you outline the points of contact and the forces being produced. For example, the contact between the hand and the box is here. That would be a force vector or arrow directed rightward, F push. And let's give F push a generic value of 100 newtons. You also have contact between the box and the ground. You also have that Newton's third law force, which reacts upward. Doing a nominal effort, I'm not really following my own advice here, to draw force vector arrows to be representative of their numbers. I suppose this should be a little bit shorter. And that's a perfect free body diagram for all the forces being described in this motion. You'll notice that there's no friction because we've established that this is a frictionless surface. You may be tasked with, hey, what's the net force in this situation, and what's therefore the net acceleration? To solve for the net force, you sum up all of your forces acting in all directions. Because gravity and normal are equal to one another, it's as if we cancel them out. They are not a factor in the net force. Therefore, your net force in this situation would be 100, technically 100 plus 0, but there is no friction, so we can just say it's 100. So if you're tasked with solving for the acceleration experienced in this situation, you can just load up force net is equal to mass times acceleration, or in this particular instance, 100 is equal to mass times acceleration. Acceleration is equal to 5 meters per second squared. But what if there is friction? Well, there's two types of friction that we come across in AP Physics and just physics in general. You got your static friction and your kinetic friction. Static friction is a much larger number. Static friction is the friction that you overcome in order to set the object in motion. Kinetic friction is the friction that you've overcome in order to keep the object in motion. If you ever had the experience of pushing a large cart of groceries or a filing cabinet, you know that it takes more force to get you going and less force to keep you going. In large part, we deal with kinetic friction because in large part we talk about objects that happen to be in motion. Let's say that our two coefficients of friction are given below. Coefficient of static friction is 0.4, coefficient of kinetic friction is 0.1. There are no units next to coefficients of friction values. They just simply are. You might be tasked with solving for, hey, when we're applying the same force to this box of 100 newtons, draw the free body diagram and solve for the acceleration experienced by the box with regard to its static friction. Well, with regards to its static friction, your free body diagram would look like this. Gravity, let's be clear about that gravity. Center of mass of the object being pulled down. Your normal force technically is exerted here. I'll draw it over here. And those will be equal to one another. Okay, so in the vertical direction there are the forces balance out. Your push force is given as 100 newtons. The push force is given as 100 newtons. Let's talk about that friction. How do we solve for it? Well, in the case of the static friction, the friction that we overcome in order to get this box moving, I guess it technically should be shown exerted here and then being that way. That would be our force of friction if we're drawing it very specifically. The equation which relates to forces of friction is forces of friction is equal to your normal force times the coefficient of whatever friction that you're dealing with here. In the case of this problem, we can solve for the force of friction as follows. Normal force is 200. Coefficient of static friction is 0.4. Initial or static force of friction is equal to 80 newtons. Therefore, what acceleration is instantaneously experienced by the box? To solve for acceleration, remember, net force is equal to mass times acceleration. In this particular problem, we know that our net force is equal to 100 minus 80, or 20, because the vertical components of force balance out. Your mass of the box is equal to 20, and therefore your acceleration would be equal to 1. Acceleration is equal to 1 meter per second squared. Instantaneously in order to get the box moving. But let's say we keep the gas down and keep applying this push force of 100 newtons to that box into the realm of kinetic. Now your kinetic friction we can solve for. Normal force times coefficient of kinetic friction. So now our force of friction is equal to 20 newtons. It's two different free body diagrams as it pertains to the two different situations, dealing with kinetic friction or dealing with static friction. In this particular case, what acceleration is experienced by the box or block? Well, your net force in this case would be equal to 80. Solve for acceleration. Acceleration is equal to 4 meters per second squared.